Welcome to the Center for Astrophysics Colloquium series. My name is John Raymond. It's a great pleasure to introduce today's speaker, Dr. Leonard Strawn from the Naval Research Laboratory. Leonard did his undergraduate work at MIT and then came here in the 1980s as a graduate student at Harvard. He worked on a project satellite to observe the solar corona in the ultraviolet led by John Cole at that time. It was a Spartan experiment, which means that it is something which is a free-flying satellite. The astronauts take it up on the shuttle, drop it overboard, collect it again in 2 weeks and bring it back down. So it has all the advantages of a rocket, but it gives you 2 weeks of data rather than 5 minutes. The instrument was in the vacuum test chamber when Leonard got word of the Challenger disaster, which of course set everything back for years. And a little bit later, he got called into the Navy to fulfill his ROTC obligation. While he was in the Navy, he finished writing his thesis on the instrument for the Spartan experiment and on some analysis of Lyman Alpha data from a rocket flight. He spent about another year in the Navy and then came back here to SAO, where he was in time to watch the first launch of the Spartan payload. I think it was launched 4 times. And after that, he joined the UVCS team to build a more powerful UV instrument to observe the corona from the Soho satellite. Leonard played a very important role in almost every aspect of the UVCS program. And after UVCS was shut down, he went to NRL in 2014. Since then, he's continued to work on space-based observations of the sun and the solar corona in particular. And he's the PI of a project called UVSC. I expect he'll tell us about that in his talk today, which is titled The Remote Sensing of Solar Energetic Particles from Coronal Shocks. Leonard.
Thank you. One small correction, I did 4 years in the Air Force. Now I'm a civilian working for the Navy. So this talk was originally supposed to be scheduled after the launch. We had a February launch for the ultraviolet spectrochronograph Pathfinder, but due to some issues with the spacecraft bus, things were delayed. And so I'm giving a presentation primarily talking about what we expect to see and what are some of the motivations for doing this experiment. Okay, so there's the title for my talk. But before I get into the UVSC Pathfinder, say a little bit about Earth Day, since today is the 51st anniversary of Earth Day. And as some of you may know, the older folks, this picture was taken during the Apollo 8 mission. It was one of the inspirations for Earth Day because it shows the planet as a global system. However, there was another experiment that was also on the moon that was an experiment by George Carruthers, who was an NRL scientist who took the first Lyman Alpha image of the Geocorona, which is the emission that you see here, showing a crescent sunlit Earth with the sort of uniform haze around it is from Lyman Alpha that's scattered from neutral hydrogen in the Earth's exosphere. And that's hydrogen primarily produced by dissociation of water vapor in the outer atmosphere. This is a paper that George wrote about that experiment. And it turned out that this particular image was also taken on Earth Day in 1972. So it was the very second Earth Day. And George unfortunately passed away last December. He was one of the more illustrious scientists at NRL. And before he passed, he was awarded the National Medal of Science from President Obama. Another thing that happened during the first Earth Day, which was 1970, shortly before that, there was a Lyman Alpha observation made of an eclipse, which took place along the eastern seaboard of the US. And this experiment was what launched John Cole's career in doing UV astronomy of the corona. With this experiment, they detected Lyman Alpha for the first time in the extended corona. It had been observed earlier on the disk of the sun, but this was the first time it was observed far out in the corona. And John Cole, as a young postdoc at the time, was given the challenge of building an instrument to observe the Lyman Alpha corona outside of an eclipse. That was the origin of the experiments that we're going to talk about today. So John Raymond talked about the Spartan experiment, which was a successor of the first rocket chronograph instrument that John Cole developed. And so I came on board after the last rocket flight, which was, I believe, 1981. I started my graduate work in 82. And then from that, we did the Spartan experiments. We actually had 5 launches of Spartan. And then from there, John Cole was selected to build the Soho UV chronograph. And that was the last orbiting chronograph of this type until this current experiment. So now I'm going to talk about the motivations. So UVSC Pathfinder, rather than looking at and diagnosing multiple ions in the corona, it's only focused on Lyman Alpha. And the reason why we chose that line is that that line is coupled to the neutral hydrogen in the corona, which through charge exchange can give you a measure of the proton distribution in the corona. And the Navy in particular is interested in the origin and the intensity of high energy proton events that are emitted from the sun. And so what I'm going to show you is a period back 1.5 solar cycles ago where we had a lot of activity on the sun. And this particular period was very active. As I play the movie, you'll see coronal mass ejections going off all around the sun. These are large volumes of gas that are being expelled from the sun, along with magnetic fields from the sun. Occasionally, these coronal mass ejections come out at very high speeds. And when they come out fast enough, they can create shock waves that entrain particles and actually accelerate those particles to very high energies. So what you see when you see the snow on these chronograph images, those are actually energetic protons that are actually hitting the camera that is used to take this picture. This is the LASCO instrument that was aboard the Soho satellite. And so this is a marvelous example of showing you all the different types of solar wind, not just the background solar wind, but also coronal mass ejections, and also the energetic particles, which is the subject of our study. So we would like to understand where these energetic particles originate and how they are accelerated. The picture that we've come up with by taking examination of all the observations in different wavelength bands, including radio, ultraviolet, visible light, etc., is this picture of a shock front that is ahead of the CME that is going at superalfanic speeds. As the shock front expands into the outer corona, it picks up seed particles that can bounce back and forth around the shock front and eventually be energized to very high energies. And by high energy, I mean basically anything above 2 to 5 million electron volts. And so the question is, how does this process happen, and whether or not it can be detected remotely? Some of the evidence that we have that this process is occurring is due to the fact that many CMEs that erupt from the sun do not produce solar energetic particles. However, we do know that as the speed of the CME increases, there's a high likelihood of producing SEPs. So the plot that you see in the bottom left shows you basically SEP flux or fluence versus CME speed. You can see that there's a nice linear correlation showing that for large speeds, for CMEs, you get more, or a more intense SEP flux that comes out. There's also evidence that when you have multiple CMEs going off, for example, in the diagrams at the right, you have a CME that is first expelled from the sun, and then a few minutes to maybe an hour later, you have a second CME that goes off. And those CMEs can actually interact with each other and produce particles that can be accelerated around the shock front. There's other evidence that supports the idea that you have shock accelerated SEPs, as opposed to traditionally SEPs were thought to be produced in flare events. However, there's now known to be two distinct types of SEPs. So this slide, which was produced by Quinn Ko, shows you the differences between these two broad categories of events. So on the left, you see what are called gradual events. These are the events that produce the longer duration SEP events. They tend to be also have a higher SEP flux. And we believe that they're produced along a long section of the CME front that has a broad longitudinal extent. And that's one of the reasons that these things are, that the duration of these things are extended. On the other hand, for flare-produced particles, we think that the basically it's the impulse from the flare itself which can produce acceleration, or even the reconnection that takes place when the flare is first released, can produce particles that can be accelerated to MEVs. So the right plot shows you a very narrow peaked event, which we believe to be due to flaring that takes place on the sun. There are also differences in the abundances. The abundances for flares tend to be enriched in helium-3, and that's also a clue to their source regions in the corona. So now I'm going to briefly talk about how we believe that these particles accelerated. This will be just a top level sketch. But basically, we believe that the acceleration process requires a population of seed particles, which are particles that are hotter than the background corona, but not quite at SEP energies. And in addition to the seed particles, the shock itself has to be strong enough in order to accelerate these particles. And so what I show here and in the next few slides are what are some of the properties of the shock that are necessary in order to produce the most intense SEP events. So we think that these particles are produced in shocks. It's not clear if the shocks are perpendicular or parallel shocks, but most people believe that the shocks that are quasi-parallel, which are configurations where the magnetic field is along the flow velocity of the shock or perpendicular to the shock front. So in the nearly perpendicular case, you have the magnetic field, which is basically perpendicular to the shock front itself. And in that situation, you have particles coming in from the left. As they approach the shock, they can be energized just due to the fluctuations in the magnetic field lines. And the fluctuations can actually increase the gyro frequency of the particles and giving them an increase in kinetic energy, as shown by the bottom plot. You see the velocity, or in this case, the kinetic energy increase as it goes through the shock front. The other case for a quasi-parallel shock, you have the magnetic field going basically perpendicular to the shock front. As the shock moves into the unshocked plasma, the particles either run into turbulence that's created by the shock itself, or by interactions between the particles and the shock can also generate turbulence behind the shock. And so what this turbulence does is create places where particles can basically bounce off of the shock. And if they have enough energy, they can bounce back across the shock into the upstream region. And by the growth of the turbulence region, you can get a lot of back and forth bouncing in the shock. And that can gradually increase energy from the superthermal range up into the MEV type range. And so these are the two mechanisms that are favored. As I said, most people favor this quasi-parallel shock mechanism, also known as diffusive shock acceleration. So one problem that exists for getting the particles to bounce back into the upstream region of the shock on the other side of the shock front is that they have to have enough energy. Normal background solar wind particles won't have enough to be injected back into the shock. So the idea is that you have a reservoir of superthermal particles that exist prior to the shock passage. And some of the sources that are believed to be responsible for the pre-existing seeds could be flares that are constantly going off and releasing superthermals. It could be reconnection events higher up in the corona, or it could be, as I mentioned, previous CME shocks that may have gone off before the shock that actually produces the large SUP. One description of a superthermal population is to use something called a kappa distribution. The kappa distribution is basically it's sort of like a Lorentzian distribution. It's a Gaussian that has wings. The kappa is a parameter that's used to define the width of the wings. And so you see in this plot here, you see a distribution which is a Maxwellian, which is on a log scale shown as a parabola. That has a kappa of basically infinity. As kappa goes to lower and lower values, you can see 10, 20, 10, 5, the wings get broader and broader. And so these type of distributions are useful for describing the population of pre-existing particle energies that can be used in models for SEPs. Some of the, well, let's say a particular model that was done when we first started to look for these superthermal particles with the Soho instrument is shown here on the left. This is a model that Steve Kramer made, which shows different values of kappa versus basically particle velocities. And you can see as kappa increases, you get a range of particle velocities depending on the amount of seed particles that exist in the background corona. And so the contours show populations going from basically 10 to the minus 5 on the extreme right to a tenth of the total plasma population when you get to the lower values. And so Kramer found that if there's a range of values where the seed particle population is above about 10 to the minus 3, that would be sufficient enough to give you the observed SEP particle fluxes that you see from CMEs. So this is just one example. More recent examples are from models that were produced at NRL by Ng and Weems at Goddard. This shows what happens when you have seed population of 0.1%, which is 0.01% on the left and 0.1% on the right. This shows what happens when you have alphanic waves that are generated at the shock due to plasma particle interactions. As the shock proceeds through the background plasma, you get an increase in the wings as a function of time. So the color curves here shows what happens as the shock proceeds from about 7 seconds out to about 500 seconds. So you can see that there's a growth in the tails. However, the growth is much more pronounced when you have a higher density in the background, a higher density of superthermals in the background plasma. And this is, again, another model that Martin Lamming made, which shows what happens when you have self-generated turbulence in the shock. So he came up with a relationship between kappa and the Mach number and the shock angle in the plasma. And so with this type of model, it gives you in a phase space the regions where you expect to get more particles energized in the shock. So for example, in the diagram at the left, you have a Mach number of 2. And you see that everywhere in the gray area of the plot, you do not get a growth in the size of the wings. And so therefore you wouldn't expect a very large yield of solar energetic particles from that. But if you look at areas where you are at smaller shock angles and lower kappas, you can get a growth of the wings. And the growth is shown by the contours in the diagram. On the other hand, at higher heights in the corona, where the alphane speed is dropping as you go up in height because the magnetic field is decreasing, for a shock that's accelerating, you can get a higher Mach number. In this case, you have a Mach number of 4. In this case, everywhere in the phase space diagram, you get a growth in the number of particles in the wings of the profile. And so you can see that by measuring different kappas in the corona and having information about the geometry of the shock, say from a white light chronograph observation, you can see that you can begin to set some constraints to different models for accelerating these particles in the shock. So enough with this is sort of a top level description of why we think the particles are there and how they may be energized. So the next part of my talk is going to be primarily on the observations, how do we make the measurements, and what's the likelihood that we'll actually be able to do make these type of measurements. So what we need to do then is convert a velocity distribution, which is described by this formula here. This is a 3D velocity distribution. We need to convert that into a profile. And the way we do that is basically we look at a line of sight observation through the corona. That line of sight observation basically gives you a measure of a velocity distribution, but that's just along the line of sight. So we have to basically convert this 3D velocity distribution into a 1D velocity distribution. And then just using the Doppler relation between velocity and wavelength, we can come up with a wavelength which gives a measure of the 1D velocity distribution through the corona. So in this next diagram, I show you what was done previously with the Soho chronograph. This is an example of a profile measurement. You can see that the profile, the actual corona profile is not symmetric. You have to actually model the scattering of the disk radiation from the source region of Lyman Alpha, which is the chromosphere transition region, do the scattering in the corona, and then add your instrument profile broadening. Because we have a finite slit, we have finite pixels, the profiles are broadened. You also have to add the effects due to the fact that you have scattering within the instrument due to diffracted light that's scattered from the occulting edges. You have also non-specular scattering from your optics. And so in a very careful analysis that was done, I want to say this is probably like probably 1999 or 2000. The UVCS Soho observations showed that after accounting for all of the corrections in the profile, they got a profile which is basically what you would expect without a kappa. However, the fact that there was no significant departures of the Maxwellian distribution could have been hidden by the fact that these profiles were obtained over many, many days. Observations were co-added to give you enough signal in order to get the profile. And so one of the things that this new experiment is going to do is to increase the effective area so that these observations can be made in a much, much shorter time frame. And so now I'm going to talk about the current experiment. So as I mentioned, the goal is to characterize the wings of the Lyman Alpha profile. And these wings would be a reflection of the velocity distribution of particles in the corona. The secondary goals of this experiment is to measure the proton kinetic temperatures. That's obtained by measuring the shape of the core of the profile. And then the electron kinetic temperature was a secondary goal because we knew it would be very difficult. But because we have the large area and which would give us a high count rate, we thought that we might have a chance of measuring that. We're also demonstrating for the first time a new type of chronograph that I'll show you in a minute. So instead of having a single occulter, we stack multiple occulters to give you an increase in the effective area. And so this is a layout of the instrument. You can see that there are 5 external occulters, 5 internal occulters, a large telescope mirror. This is 13 centimeters by 7 centimeters, which directs the light from the corona through a slit where it hits a diffraction grating, and then it goes to a detector. And these are some of the properties for the instrument. The fact that we have 5 external internal occulter pairs lined up gives you the ability to have a very large collecting area. I'll show you in a minute why this is important, because normally for a typical meter-sized coronagraph, you're not able to get a very large amount of mirror area just due to the vignetting of the mirror due to the internal and external occulters. So traditionally, chronographs, I should say an externally occulted chronograph gives you a very narrow geometric area. And that's just because you're looking very close to the occulter edge. You know, the height ranges that we're looking at are just a few solar radii, which is only you know, a couple of arc minutes or so. So in that very, very narrow range, you get a very small amount of light on your mirror. One way to increase that area is to go for a longer chronograph. And so on the bottom image here, you can see that by extending the baseline between the occulter and the mirror, you get a much larger area for your observations. And this is typically what was done for many of the instruments that were proposed after UVCS Soho. So you can see that UVCS had a 1.7 meter baseline. In order to increase the area to get higher count rates, we proposed missions over the years. ASCE had a 14.8 meter boom. Another mission that was proposed had a 12 meter boom. More recently, we proposed a Lockyer mission, which had a 10 meter boom. And all of these missions gave you a much larger geometric area compared to Soho. However, we can get the same increase in area by using a smaller chronograph that's only 1 meter, but using 5 occulters. And so you can see here that we can get the same basic geometric area with less, I should say, with a shorter baseline, which leads to a much more compact chronograph. And so this is what the interior optics of the chronograph look like. So the light comes in from the left, and you have 5 external occulters and 5 internal occulters that hit the mirror. One of the issues that we have is that because we're using a fixed telescope mirror, that means that the light coming in from different coronal heights, different solar radii, they will come off of the external occulter at different angles. And that diffracted light still has enough signal. There's enough scattered light in there that can still overwhelm the coronal background observations. And so what we have to do, traditionally we block that edge there with an internal occulter. And so you can see that in this geometry here with the, I'm just taking one of the slits here, one of the slots. The blue lines show light coming from the extreme edge of the external occulter and light coming from 3 solar radii. That light is blocked by an internal occulter, which is extended into the light just so that it over occults this external edge here, so that you can get light coming in that has predominantly coronal radiation. Now, light coming at a different angle, say from 1.8, would have light scattered from this edge here coming in at a different angle. And that requires an internal occulter, which is at a different position at the internal occulter slit. So for that, we use this internal blocker here. And so what we have to do now is ensure that scattered light from all of these edges here, from both the external and internal occulter, are reduced so that you can still get you can still observe what we estimate the background coronal signals should be. And so by modeling an extended sun with Fresnel diffraction off of all of these edges here, you get a residual diffracted light that's about 10 to the minus 8 of the coronal radiation when you're at 1.8, and about 10 to the minus 9 at 3 solar radii. This is more than adequate to measure the core profile. And it's adequate also to measure the extended rings of the profile. However, there are some caveats there that I'll talk about next. So this is an example of a coronal profile at, I believe it's at 1.8 solar radii. The solid line gives you what's observed at the detector, which includes the input profile from the Coronal, which is this dashed line, which is Gaussian with a kappa 3.5, that 10% population kappa 3.5 convolved with a Maxwellian profile. And then you see calculations for scattered light from the diffracted edge, which is the dotted line here. You see contributions from gradient scatter, which are the dashed dotted lines here. And we use two different estimates depending on what the scatter is on the what the micro roughness is on the mirror. And then we've also added this very broad electron scatter contribution, which is a 40 angstrom 1/E half-width line, which is constantly present in the corona. And so what you get here is basically a profile that can give you enough information about the kappa, the magnitude of the kappa, assuming that you can integrate all the radiation in the wing and compare that to a model of the profile without a kappa in that same bandpass. And so originally we had decided that we could measure individual points on the profile. However, after looking at a number of models, we now feel that the best way to determine the measurement is to do an integration from, say, 1 to 3 angstroms in the profile wing and compare that total intensity to a modeled intensity in the same bandpass, assuming that you don't have a kappa. And that will give us the strongest evidence for measuring the size of the kappa. And so what I show here is a model profile showing a kappa distribution versus a profile without a kappa. And you can see that there is a measurable difference in this region between say 1217 and 1220 angstroms. This is a log scale, mind you, but still it's the integrated area that we're concerned about, and that is something that we believe is measurable. I want to say a little bit about where these observations are coming from. We have 7 slits in the instrument that measure light from 1.8 and 3 solar radii. We don't have the ability to roll the instrument, unfortunately. So these were fixed on the west limb of the sun. And the reason why the slits are segmented is so that the spectra from each of the slits do not overlap on the detector. And so this gives us a way of getting profiles at 2 heights simultaneously, which would be useful for looking at how the shock develops as it propagates away from the sun. And we can also look at how the shock parameters change as a function of the background plasma parameters. And so we have basically many of the diagnostics that you would want for determining the plasma. We can measure, as I said before, the temperatures based on the Lyman Alpha profile gives you a measure of the proton temperatures in the corona. The total integrated flux can give you a measure of the number density. And you can also use cotemporal white light observations and also magnetic field modeling to give you an idea of the plasma angle, the shock angle measured in the corona. And so by combining models and the plasma parameters that are derived from the observations to use as input into those models, we are hoping to get a fix for whether or not these seed particles exist. One thing I should say is that we're launching during a time of solar minimum, and that means that we have fewer CMEs going off, but we can still determine seed particles without CMEs being present. In fact, that makes the observations even easier. Ideally, though, you want to have your measurements nailed down without a CME, and then hopefully, if there is a CME that goes off, you can measure, say with in situ instruments, either at 1 AU or even solar probe or solar orbiter. If they measure an SEP event while we're doing the observations, we can make some comparisons about the strength of those events and compare those as whether or not there's a large or small seed particle population. And so that's the primary goal of the experiment. That's the primary science goal. We also would like to demonstrate whether or not this type of chronograph is actually viable. If it is, then this would be an easy way to get a large collection area without having to go with a long boom. That would therefore reduce the cost of the instrument because it'd be easier to build. And a smaller instrument, more compact, lower cost, means that you could make more than one of these at a reasonable price. And that will allow you to have multiple sensors looking at the corona, possibly in different orbits, not necessarily an Earth orbit. And that would be the beginning of something that could be used for a space weather forecasting system. And so finally, I just want to thank all the team members that have contributed mightily to the project. We have a team of modelers, observers, and people that are the bulk of the team that actually built the hardware and did the testing. And so we think we have a nice combination that would be put to bear on exploiting the data. And finally, I just want to thank John Raymond and Lars and the Colloquium organizers for inviting me to give this talk. So after that, I will take any questions.
Thank you, Leonard. That was really an impressive satellite you have there. And I hope maybe we can hear you again after it's actually been launched. So people who have questions can raise their hands, and I hope I will be able to see them. Use the reactions button. And in the meantime, let me ask one question to begin with. The observations of the line core will be really a great complement to the METIS Lyman Alpha coronagraph imager, which is on solar orbiter. So I was wondering if you have any plans for observations that are coordinated, or do you just do essentially the same observing program all the time?
Yes, we basically will do the same program. It's a sit and stare mission, basically. And as I said, unfortunately, because we don't have a roll capability, we're going to count on the fact that the Earth's orbit is inclined. The orbit and the equator is inclined to the solar equator. So over the period of a year, we'll get different latitudes from the solar equator. And that will be the only variation in the observation. So essentially, we're basically collect data.
Great. Let's see, there are a number of questions. How about Giovanni?
Yeah.
I see his hand is raised.
Okay. Yeah. Can you hear me okay? Yeah.
Yep.
Yes,
Hi, Leonard. Good to see you and welcome back again.
thank you.
It wasn't clear to me whether the Fermi mechanism for particle acceleration in a shock wave was related to the mechanism that you proposed, or is it something different? Could you comment on that?
I'm going to ask Martin if he can comment on that. I believe that the diffusive shock acceleration is a first order Fermi acceleration.
Yes, it's right. It is first order Fermi at the quasi-parallel shock going round to perpendicular shock, strictly perpendicular shock, something different happens, shock drift acceleration, but it's basically Fermi acceleration, first order Fermi.
Great.
Okay, thank you. Thanks.
And Shadia has her hand up.
Yes, so Leonard, that was a great talk. I really appreciated it. So I wouldn't give up on not seeing CMEs because during the eclipse of 2020 in December, there was an incredible CME. So that's just two. The other question I had is, do you expect to see kappa distributions for heavier ions, or is it just for the most visible and for protons?
We don't have very many lines in the bandpass. We're basically looking at Lyman Alpha plus or minus 100 angstroms. So there's an iron 12 line, I believe, 1242. There's a silicon line and a couple others, but they're much, much fainter than Lyman Alpha. So it would be a challenge to try to get enough counts in those profiles to measure departures from Maxwellian.
Well, I was thinking that if we could try to do that with our eclipse observations.
Yeah, I mean, if you look at the distributions, you'll see that they're like, 3 orders of magnitude fainter than the peak of the line. You've got to have a really well-characterized background so that you can remove that to get to the level that you would need to see the departures from Maxwellian.
Thank you.
Okay, and Angelos is next.
Hey, Leonard, a couple of quick questions. One is what drove the selection of 1.8 and 3 for the heights for the UVSP?
Those heights was selected based on where we think we see CME shocks formed. You've done a lot of work on this with white light observations of CME shocks. So the idea was to try to get something in the regions where the shocks are first formed.
But do we really require a shock for this, or just compression will do? Will compression drive kappa distributions?
I'm going to have to let Martin answer that. I don't know.
The 1.8 and 3 were chosen to be roughly before the shock, before the disturbance seeps into a shock and afterwards.
Uh-huh.
The kappa distribution we're looking to see is independent of the shock. It's there before the shock erupts. And we just want, you'd like
Yeah,
to
but
observe,
do we need a shock to create the kappa distribution?
No, the kappa comes from something else, presumably from reconnection.
Ah, okay. Gotcha.
I don't think it does come from a shock, because a shock in general cannot produce the steep enough, the hard enough spectra to successfully inject particles into the acceleration mechanism, but reconnection can.
Thank you.
That's what we're thinking anyway.
Okay, excuse me. And we have a, oh boy, we have a question from Silvano Fineschi.
Ciao, Leonard. Very interesting talk. Thank you. I have a comment and a question. The comment goes along the lines of what John was saying, John Raymond was saying regarding the complementarity with METIS. I mean, be very, very critical for also for the, as you know very well, for the Doppler dimming technique used by METIS to know the electron temperature. So just knowing that would be a great, actually that would be the first measurement, let alone of course the seed particle. Then the other question, the question is, can you explain to me a little bit better the internal blocker? I don't know if you...
Yeah, let me see if I can go back.
I mean, it's a very sleek design, the entire.
Yeah, so if you remember for UVCS on Soho, we had a movable internal occulter. And so as you look at different heights in the corona, you can pull back the internal occulter higher and higher, because you're looking, basically, you're looking around the external occulter. Because we have a fixed mirror and a fixed internal occulter, we have to actually put a blocker at 1.8 simply because we can't move.
Okay. So it's like a wire, like a thin strip or something like that?
Yeah, we have a thin strip, which basically is in the field of view of the 3 solar radii observation. Here, because that slit is wide enough to give you enough light. But when you look at the 1.8 observations, you're only looking at a smaller part of the internal occulter slot, if you will. And that's necessary because, as I said, just the diffracted scattering off of the edge of the external would be your observation.
Thank you.
Okay, and I think we have time for one more question. Marco Romoli.
Yes. Can you hear me?
Yes.
Yeah, okay. Hi, Leonard. Nice talk. I have a question regarding the background light. How do you determine that? Is that measured on ground, or you have a plan to measure it also in flight? Stray light and...
Yeah, we're going to do some stray light characterization by, we can off-point the instrument because we have our own gimbal mechanism. And we can also look at backgrounds away from the sun. And also, we're going to try to characterize the Lyman Alpha Geocorona, which will give us the narrowest line that we can measure, and also give us an idea of what background is. So we have to sort of bootstrap our way to what all the backgrounds are, since they weren't all characterized on the ground. And we cannot, for example, look at the disk directly. And so we have to use the Geocorona We have to use star observations, for example, to update the efficiency of the instrument. And, you know, there are going to be some parameters that we won't be able to measure, but we'll have to try to characterize them as best as we can. And the non-specular scatter can be best characterized by the narrowest line that we can use. And that would be either a narrow coronal line or the geocorona.
Okay, thanks again, Leonard, for a wonderful talk. And thanks everybody for attending. And I believe we have one more colloquium left in this series. So goodbye.